Hi there, this video is all about the finite element method, which is one of the most popular methods for numerically solving differential equations. Over the years of research, many brilliant ideas have brought the finite element method to the computationally efficient state that it is now. Studying all these sophisticated ideas at once can be very overwhelming, which is why in this video we will explore the finite element method across 3 levels of increasing complexity. Before we start talking about the finite element method, we need to define a problem that we want to approach with the finite element method. So let's have a look at a particular differential equation. We will consider the so-called Poisson problem in one dimension, which states the following. For a given function f of x, find a function u of x such that its second derivative, which is here denoted by u double prime, is equal to f of x. We are interested in the unknown function u of x on the interval from x equals to 0 to x equals to 1. And we consider the boundary conditions that u at x equals 0 is 0 and the first derivative of u at x equals 1 is 0. Let's visualize this. We have given a function f of x. In this video, we will assume that it is constant, and we will denote its constant value as f bar. We are interested in the function u of x, and we are also interested in its first and second derivative, which describe the slope and the curvature of u. The function u of x and hence also its derivatives are unknown. Our goal is to find a solution function u of x such that u and its derivatives fulfill the differential equation and the boundary conditions. For this simple problem in 1D, it is possible to find an analytical expression for the solution function. By illustrating this function and the derivatives, we observe that this function is indeed a solution to our problem, because the second derivative of u is equal to f of x, and the boundary conditions are fulfilled because u at x equals 0 is 0, and the first derivative of u at x equals 1 is 0. In practice, however, when we consider more difficult differential equations in higher dimensions and on complex geometries, deriving the function u of x analytically is not feasible, and we need computational methods like the finite element method to approach the problem. So let's start talking about the finite element method. Using computers for solving mathematical problems has revolutionized the natural and engineering sciences. However, computers have one major drawback. They are designed to solve problems in finite dimensions. This means that the result of a computer program or algorithm always needs to be expressed by a finite set of numbers. The unknown of a differential equation, in our case u of x, is a function, and the function is an infinite dimensional object, which in simple terms means that the function u of x is unknown at infinitely many points between x equals 0 and x equals 1. Therefore, it is not trivial to approach such kind of problems using computers. This is where the finite element method enters. The core idea of the finite element method is that we don't assume the entire function u of x as unknown, but instead assume that the function is unknown at a finite number of points in the region of interest. The points at which the function is assumed unknown are called nodes. Between the nodes are the so-called elements. Notice that we have a finite number of elements, each with a finite size, which is the reason why the method is called finite element method. Between the nodes, we assume that the function can be described by very simple predefined functions, which are called shape functions. Here you can see an example with linear shape functions, but higher order polynomials are also possible. As the shape functions are known, it is sufficient to know which values the function takes at the nodes to know which values the function takes everywhere. Thus, the entire information about the function and how it looks like is compressed to a finite number of numbers. Reducing the original problem with infinitely many unknowns to a problem with finitely many unknowns is called discretization, and it introduces a systematic error, known as discretization error. However, it can often be shown that the discretization error decreases upon increasing the number of elements, which is called convergence. But let's try to better understand the concept of discretization using formulas and a concrete example. For each node, we define one shape function n of x, which is respectively 1 at one node and 0 at all other nodes. The index of n indicates at which node the shape function is 1. Let's take a look at the shape functions individually and describe the shape functions more rigorously using formulas. The first shape function is linear on the first element, that is between the node x equals 0 and the node at x equals 0.2. On this element, the shape function should be equal to 1 minus 5x, which computes to 1 for x equals 0 and to 0 for x equals 0.2. On all the other elements, the shape function is 0. Let's proceed with the next shape function. The second shape function is linear on the first and second element, which is described through the functions 5x and 2 minus 5x respectively. And on all the other elements, the shape function is 0. We proceed like this for all shape functions. If you like, pause the video and construct the shape functions n3, n4 and n5. After having defined all shape functions ni, we assume that the unknown function u of x can be expressed as a linear combination of the shape functions, which means that it is expressed as the sum of some unknown scalar parameters ui multiplied by the shape functions ni. In this way, the parameter ui dictates which value the function u of x takes at the node I. By tweaking the parameters ui, we obtain various shapes. As you can imagine, if more elements are considered, the variety of shapes that can be expressed with the ansatz would increase. After having defined the ansatz for u of x, our goal is to compute the unknown values ui. A seemingly logical idea would be to substitute the ansatz into the given problem and solve for the nodal values ui. But there is a catch, which becomes clear when illustrating the ansatz and its derivative. We have designed the ansatz in such a way that the second derivative of u is always 0. This means that the differential equation cannot be fulfilled, no matter how we choose the nodal values ui. The way the problem is formulated here puts very strong requirements on the solution function. It is therefore also called the strong formulation of the problem. To tackle the problem with the finite element method, the problem must first be reformulated into a mathematically equivalent formulation, which is called the weak formulation of the problem. I will not dive into details here, but here's a quick summary of what needs to be done. We introduce a type of functions which we call test functions v of x. The test functions are, like u of x, defined on an interval between x equals 0 and 1. And they may take any arbitrary shape on this interval. Then we multiply both sides of the differential equation by the test functions. And afterwards we integrate both sides of the equation over our region of interest. Finally, we apply the concept of partial integration to arrive at an integral equation that must hold true for all test functions that are 0 at x equals 0, with the additional constraint that u at x equals 0 is 0. Now let's hold on for a bit. This derivation of the weak formulation was very fast, and I left out many details. The concept of the weak formulation is not trivial, and being puzzled right now is completely normal. I felt the same when I saw the weak formulation the very first time. Therefore, I made an entire video about the strong and the weak formulation and how they are related. And I encourage you to watch it if you are interested in a deeper understanding of the topic. For the rest of this video, it is important to observe the following. We have transformed the strong form, in which the differential equation must be fulfilled for all points x in our region of interest, into a weak form, which is an integral equation that must be fulfilled for all possible test functions v of x. And we further observe that our unknown solution function u of x appears with its second derivative in a strong form, but only with its first derivative in the weak form. Therefore, the finite element ansatz, which we could not substitute in the strong form, can be substituted in the weak form. So let's substitute the finite element ansatz into the weak form. As the derivative of u appears in the weak formulation, the ansatz must be differentiated. This is not difficult because the parameters ui do not depend on x, and therefore the derivative of the sum of ui times ni is the sum of ui times the derivative of ni. Notice that the weak formulation also contains the test functions v of x. As I explained earlier in this video, computers are not designed to work with infinite dimensional objects like functions. Therefore, we also have to discretize the test functions. And it is common practice to use the same shape functions as we have used for discretizing u of x. Before we substitute the ansatz for u and v in the weak formulation, we will slightly change the notation. To this end, we introduce the vectors U and V, which contain the nodal values of the functions u and v respectively. And we introduce the vectors n and n', which contain the shape functions and their derivatives respectively. This allows for a more compact representation of the ansatz for u and v. Finally, we can insert the ansatz for u and v in the weak formulation. Quantities that do not depend on x, like U and v, can be written outside the integrals. We notice that the integrands of the integrals are known quantities. Therefore, these integrals can be computed. How this is exactly done will be discussed in detail later in this video. For now, we will only notice that n' is a vector and thus n' times n' transposed is a matrix. Thus, the integral on the left-hand side of the equation is a matrix, which we will denote by capital K. The integral on the right-hand side of the equation is a vector, which we will denote by capital F. We then obtain the equation v transposed Ku equals v transposed F. Let's hold on for a bit and think about how we arrived at this equation. We started from the weak formulation, which must hold true for all test functions v of x that are 0 at x equals 0, and the unknown function u of x must fulfill the boundary condition that u at x equals 0 is 0. By discretizing u and v, we arrived at the equation v transposed Ku equals v transposed F, which we could call the discretized weak formulation. Because the weak formulation must hold true for all test functions v of x, the discretized weak formulation must hold true for all vectors V. And because v of x and u of x are 0 at x equals 0, the nodal values v0 and u0 must be 0. Let's see how v transposed Ku equals v transposed F looks like if we expand the vectors and matrices. Because v0 and u0 are 0, the equation simplifies a bit. That is, the first row and column of K and the first row of F are multiplied by 0 and hence vanish. This simplified equation must hold true for all vectors v. On the left side of the equation, v is multiplied by the vector resulting from k times u. On the right hand side of the equation, v is multiplied by the vector f. If you think a little bit about it, then you will realize that the equation can only be true for all vectors v if and only if v is multiplied by the same vector on both sides, which means that k times u must be f. We finally arrived at a linear system of equations that can be solved for u. Starting from the weak form of the Poisson problem, we have used the finite element discretization to arrive at a linear system of equations. However, we have not yet discussed how the system matrix K and the system vector F are actually computed. To compute K and F, we have to compute the integrals of n' times n' transposed and minus f times n, respectively. Later in this video, we will study how to compute such integrals numerically using computers. But for now, let's do the computations by hand. Let's start with K. K is a matrix with one row and one column for each shape function. We can compute k by computing each component of the matrix separately. Writing the formula for k in index notation, we will find that the matrix component kij equals the integral of ni prime times nj prime. As an example, let's compute the component k01. To this end, we need the shape functions n0 and n1. Or to be more precise, we actually need the derivatives of the shape functions n0 prime and n1 prime. k01 is the integral of n0 prime times n1 prime. Because n0 prime and n1 prime are piecewise defined functions, that is, functions that are defined differently for different ranges of x, we apply a small trick before we substitute n0 prime and n1 prime into the integral. We split the integral from x equals to 0 to x equals to 1 into 3 sub-integrals. The first integral integrates over the first finite element, where n0 prime is minus 5 and n1 prime is 5. And the second integral integrates over the second finite element, where n0 prime is 0 and n1 prime is minus 5. The third integral integrates over all other finite elements, where both n0 prime and n1 prime are 0. This leads to 3 integrals that are fairly simple to compute. Doing this computation for each component of the matrix K would be quite boring. So here I'm just showing the result. We observe 2 things. First, the matrix K is symmetric. This becomes clear if we take a closer look at the formula of the components Kij. We observe that switching the indices I and j has no effect on the formula, which means that the Kij must be equal to Kji for all I and j. Further, we observe that the matrix K is sparse, which means that it has a lot of 0 components. The reason for this is that some pairs of shape functions n, and hence also their derivatives n prime, do not share any finite element where both of them are non-zero. Take for example n0 and n2, whose derivatives are shown here. When plotting n0 prime and n2 prime, it becomes immediately clear that n0 prime is 0 wherever n2 prime is non-zero and vice versa, which means that their product is 0 everywhere. The matrix K being symmetric and sparse means that less memory is required to store the matrix, and it is computationally efficient to solve the linear system of equations. Next, let's proceed with the vector f. In index notation, we find that the component fi equals the integral of minus f times ni. For this video, we will assume that f of x is constant and takes a known value f bar. I leave the computation of the vector f for you as an exercise. Here is the result. Finally, we set up the linear system of equations and solve for the unknown vector u. Here you can see the result, for which I have assumed that f bar equals minus 1. We observe that the finite element solution in green is close to the analytical solution in yellow, where the latter is of course only available because we are considering a very simple problem in 1D. That's it for the first level of explaining the finite element method, where we have learned about the fundamental concepts of the method. So why not end the video here, you may ask. The problem is that we have computed the integrals for the matrix K and the vector f by hand. This becomes infeasible for problems with more elements or problems in higher dimensions. We thus want to avoid calculations by hand and automate the integration as much as possible. Therefore, level 2 and 3 will be about finding more elegant and computationally efficient ways to compute K and f. Please note that this will not have any influence on the results of the method. At each level, we will arrive at exactly the same linear system of equations. Until now, we have defined the shape functions n of x for all x between 0 and 1. We could therefore call these shape functions the globally defined shape functions. To compute the system matrix K and vector f, we had to compute integrals over the entire region of interest from x equals 0 to 1. At the second level of explaining the finite element method, we explore a different way to define the shape functions. In this way, we will be able to express integrals over the entire region of interest as sums of integrals over the individual elements. The general motivation behind this is that when we solve problems with computers, we are usually interested in splitting bigger tasks into smaller subtasks, which can be solved in parallel. But there's also a more practical motivation behind defining shape functions on the individual elements, which will become clear at the third level of explaining the finite element method. To define shape functions for each element, let's take a closer look at the elements. In the following, the elements will be denoted by omega 1 to omega 5. For each of these elements, we can construct shape functions. These shape functions will be denoted as element-wise defined shape functions NEJ, where the superscript E indicates which element is considered and the index J indicates which node of the element the shape function corresponds to. Please note that E is a superscript and not an exponent here. But let's be more concrete. For the first element, we define the two shape functions n10 and n11. They are defined such that they are 1 at one node of the element and 0 at the other node. We define such shape functions for every element. Next, we use the shape functions to approximate u of x at each element. Here, ue of x means that we are considering u only at the element e, and uej are the nodal values of u at this element. We can also write this ansatz in vector notation. In a similar way, we construct an ansatz for v of x at each element. Let's visualize this. Until now, we have used globally defined shape functions and we introduced a global ansatz for u of x with these shape functions. With the newly introduced element-wise shape functions, we can introduce an element-wise ansatz for u of x. Next, we can substitute this element-wise ansatz into the weak formulation, as we have done for the global ansatz. To do so, let's take a look at the weak formulation. Before we can substitute the element-wise ansatz, we have to split the integrals that range over the entire region of interest into the sum of integrals over each element. Recall that we have already applied a similar strategy previously when computing the integral for one of the entries of k. Next, we can substitute the element-wise ansatz for u and v. We move quantities that do not depend on x outside the integrals. What is left in the integrals looks very familiar to the definition of the matrix K and the vector f, with the only difference that the element-wise defined shape functions appear in the integrands. We therefore call these integrals the element matrix Ke and the element vector Fe. We arrive at an equation which looks similar to the discretized weak formulation that we have seen earlier. The element matrix Ke can be computed for each element. Here I'm just showing the result. Feel free to cross-check these results by computing the integrals by yourself. Finally, also the element vector Fe is computed for each element. With the newly introduced element-wise ansatz, we have arrived at one matrix Ke and one vector Fe for each element. However, to be able to set up a linear system of equations, we need to know how the global matrix K and the global vector F, which we have considered at the first level of explaining the finite element method, look like. It turns out that the global matrix K and the global vector F can be assembled from the element matrices Ke and element vectors Fe. Let's take a look at the assembly of the global matrix K. To do so, we consider the left-hand side of the discretized weak formulation. We then expand the sum over all elements. Recall that each of the elements has two nodes and two unknown nodal values of u. These nodal values are related to the globally defined nodal values of u. In particular, u10 at the element level must equal u0 at the global level, and u11 at the element level must equal u1 at the global level. Similarly, u to 0 must equal u1 and u to 1 must equal u2, and so on. Taking this relation between the nodal values at the element level and the nodal values at the global level into account yields the following expression. It turns out that after rearranging some terms, we arrive at this expression. We recognize the matrix that we have arrived at as the global matrix K, which means that the matrix K can be quite easily constructed from the element matrices Ke. This step of the finite element method is called assembly. We finally assemble the global vector f from the element vectors Fe. To this end, we consider the right-hand side of the discretized weak formulation. We expand it. We relate the nodal values at the element level to the nodal values at the global level, and finally assemble the global vector f. That's it for the second level of explaining the finite element method. We have learned how we can arrive at the global matrix K and the global vector f from the element matrices Ke and element vectors Fe, which have been computed by formulating an element-wise ansatz for u and v. At the first glance, it seems that the problem is now more complicated than before. At the next and final level of explaining the finite element method, it will become clear why defining the finite element ansatz at the element level is useful. At the previous level of explaining the finite element method, we have introduced shape functions for each element separately. We then found formulas for the element matrices Ke and the element vectors Fe. To compute these matrices and vectors, we had to compute integrals over each element. At the third level of explaining the finite element method, we will simplify the process of computing Ke and Fe. To this end, we will introduce a so-called reference element. This reference element can be considered as the blueprint for all the actual elements. It is defined on a different coordinate axis, which we will call xi, and it is defined on this coordinate axis between xi equals -1 and 1. We then introduce shape functions on this reference element, which I will denote by curly n0 and curly n1. These shape functions on the reference element are closely related to the shape functions that we have previously defined. The advantage of introducing such a reference element is that all element matrices Ke and element vectors Fe can be expressed as integrals from -1 to 1. Such integrals can be computed very efficiently using computers. But before we come to that, we need to study the relation between the shape functions on the actual elements and the shape functions on the reference element. And we have to derive how integrals over the actual elements can be transformed into integrals over the reference element. To do so, we will define a mapping that maps from the actual elements to the reference element and vice versa. Here I'm showing an actual element omega e on the x-coordinate. To keep it general, I denote the left and right node of the element as a and b respectively. And here I'm showing the reference element on the xi-coordinate. Our goal is to introduce a mapping from the xi-coordinate to the x-coordinate. That is, we are looking for a function phi e of xi, which is defined in a way that x equals phi e of xi. Assuming that this function is linear, we can come up with this expression for phi e of xi. Taking a closer look at this expression, we observe that the point xi equals -1 on the reference element is mapped to x equals a on the actual element. Likewise, xi equals 1 is mapped to x equals b, and in the same way all other points on the reference element are mapped to the corresponding points on the actual element. If we rearrange the expression for the mapping phi e of xi, we observe that the mapping can be expressed as a linear combination of the shape functions on the reference element and the nodal positions a and b of the actual element. This means that we are using the same shape functions for defining the mapping phi e of xi as we are using for the finite element ansatz. This way of defining the mapping phi e of xi is called the isoparametric concept. Theoretically, one could define the mapping phi e of xi using other shape functions, but this is never done in practice. Finally, we can also define the inverse of phi e, which maps points from the x-coordinate to points on a xi-coordinate. After having defined the mapping phi e of xi, we can take a closer look at the relation between the values of the shape functions on the actual element and the values of the shape functions on the reference element. The values of the shape functions on the actual elements n, e, j of x can be mapped to the reference element by substituting x with phi e of xi. It turns out that this is equal to the values of the shape functions on the reference element, curly nj of xi. If you like, pick an element e and a node j and verify that this relation is true. As we will need them later, we also take a closer look at the values of the shape function derivatives. The derivative of nej of x with respect to x can be written as the derivative of nj of xi with respect to x. We can then apply the chain rule to arrive at the derivative of nj of xi with respect to xi times the derivative of xi with respect to x. We then invert the derivative of xi with respect to x and substitute x with phi e of xi. We arrived at an interesting result. While the values of the shape functions on the actual elements are equal to the values of the shape functions on the reference element, the shape function derivatives on the actual elements are not equal to the shape function derivatives on the reference element. Next, we will take a closer look at the element matrices and the element vectors. Recall the formulas for the element matrices Ke and the element vectors Fe. Our goal is to transform these integrals over the actual elements into integrals over the reference element. To do so, we use a concept that you might recognize from calculus. It is the concept of integration by substitution. Integration by substitution states that, given a mapping x equals phi e of xi from the xi coordinate to the x coordinate, the integral from a to b of a function g of x is equal to the integral from inverse phi e of a to inverse phi e of b of the function g evaluated at phi e of xi times the derivative of phi e of xi with respect to xi. If we assume that the mapping phi e of xi is the very same mapping that we have introduced previously, the integral limits further simplify to -1 and 1. This formula can finally be used to transform integrals over the actual elements into integrals over the reference element. So let's apply integration by substitution to the formula for the element matrices Ke. First, we expand the shape function derivatives to explicitly state that the derivatives are with respect to x. Then we apply integration by substitution. With the previously derived relation between the shape function derivatives on the actual element and the shape function derivatives on the reference element, we finally arrive at this expression. We also apply integration by substitution to the formula for the element vectors Fe. And with the previously derived relation between the shape functions on the actual elements and the shape functions on the reference element, we arrive at this expression. We have finally transformed all integrals over the actual elements to integrals over the reference element from -1 to 1. But why is this useful? Well, it turns out that integrals from -1 to 1 can be computed very efficiently using computers. To do so, we introduce a numerical method for integrating functions, the so-called Gaussian quadrature. Gaussian quadrature states the following. Given a polynomial p of xi and a set of so-called Gauss points xi I and Gauss weights wi, the integral of p of xi from -1 to 1 can be computed by evaluating the polynomial p of xi at the Gauss points and multiplying the results by the Gauss weights. This numerical method is very attractive because the integrals are not approximated but computed exactly if the right number of Gauss points and Gauss weights are chosen. The higher the polynomial order, the more Gauss points and Gauss weights need to be considered. The optimal location of the Gauss points and the values of the Gauss weights can be derived a priori and they can be stored in lookup tables. Here are some exemplary Gauss points and Gauss weights for different polynomial orders. In our specific example, we are only integrating polynomials of order 1 or less. For such simple polynomials, only one Gauss point and Gauss weight is sufficient. And the integral simplifies to evaluating p of xi at xi equals 0 and multiplying the result by 2. This formula can be interpreted geometrically. If p of xi is constant, that is a polynomial of order 0, p of xi at xi equals 0 times 2 is equal to the area under the constant function. And the formula holds also true if p of xi is linear, that is a polynomial of order 1, because the left and right triangle shown here have the same area. Gaussian quadrature comes in very handy when evaluating the integrals for the element matrices Ke and the element vectors Fe. Instead of evaluating the integrals by hand, we can evaluate the integrands at xi equals 0 and multiply the result by 2. This is a task that can be very well done by computers. But let's take a look at an example to fully understand the process. First, let's compute an entry of the element matrix of one element using Gaussian quadrature. Let's pick the first element with a equals 0 and b equals 0.2. And let's pick the entry I equals 0 and j equals 1. The mapping phi for the chosen element is 0.1 times 1 plus xi, and its derivative is 0.1. We also need the shape functions curly n0 and its derivative, and the shape function curly n1 and its derivative. By substituting everything into the integrand, we find that the integrand is minus 2.5. We finally apply Gaussian quadrature and the integral computes to minus 5. This is in agreement with the element matrix that we have computed during the second level of explaining the finite element method. Next, let's compute an entry of the element vector of one of the elements using Gaussian quadrature. We assume that f of x is constant and equal to f bar. Again, we pick the first element and we pick the entry I equals 0. We need the mapping phi for the chosen element and its derivative, and the shape function curly n0. By substituting everything into the integrand, we find that the integrand is minus f bar times 1/2 minus 1/2 xi times 0.1. Then we apply Gaussian quadrature by evaluating the integrand at xi equals 0 and multiplying the result by 2. And the integral computes to minus f bar times 0.1. This is again in agreement with the element vector that we have computed earlier in this video. After computing all entries of the element matrices Ke and the element vectors Fe, the global system matrix K and global system vector F can be assembled in the same way as described at the second level of explaining the finite element method. Let's summarize. At the first level of explaining the finite element method, we have considered globally defined shape functions. At the second level, we have introduced shape functions that are defined for each element. And at the third level, we have introduced shape functions defined on a reference element. Please note at this point that the dependence of the shape functions on x or xi is sometimes omitted in textbooks or lecture notes on finite elements. And it is common to denote the shape functions on the reference element, which I denoted by curly n, simply as n. This can make it quite difficult to distinguish between the shape functions. So try to always understand from the context which definition of the shape function is considered. At the first level, we could directly derive the system matrix K and system vector F. At the second and third level, we first computed the element matrices Ke and element vectors Fe, which then needed to be assembled to obtain the global system matrix and vector. At the third level, we have also introduced the concept of the reference element and Gaussian integration to efficiently compute the element matrices and element vectors. At all three levels, we arrived at exactly the same global system matrix and vector, and hence at the same finite element solution. That's it for this video. If you liked it, you can support me by sharing the video with your friends. Bye!